going to talk about computerized adaptive testing for cognitive diagnosis. That is CDCAT in classroom, a non-parametric approach. And I will explain why we emphasize in classroom design study and why a non-parametric approach is proposed to deal with the problem of CDCAT in classroom. And this is the joint work with my two advisors, and this is supported by NSF grant. Okay, so this is the online our study. We will focus on the DINA model in our study, and the non-parametric classification method is used to develop a non-parametric procedure for item selection in our studies. So, and we conducted a simulation study, and there is discussion. So, what is cognitive diagnosis? Unlike traditional IRT models, which have a continuous latent variable, cognitive diagnostic models have multiple latent variables, which are usually binary. Okay, so that is, cognitive diagnosis decompose the ability domain into specific subscales to measure. And so one examinee might master one attribute and might not master another attribute. So the ultimate goal of cognitive diagnosis is then to measure the mastering statuses of examinees. So let me give you some notation. The alpha is used to denote the attribute profile, and Y is the response. And there is a central element in cognitive diagnosis, which is the Q matrix. It's a binary matrix indicating the connection between the items and the cognitive constructs underlying the test. And it's usually pre-specified by experts, and we assume in our study that it's correctly specified. So, why do we need a non-parametric approach for CDCAT? First, combining cognitive diagnosis with computerized adaptive testing makes cognitive diagnosis more efficient. That is, fewer items are required to make accurate diagnosis, so it will be more efficient. And so, however, parametric methods used to select item for CDCAT mostly rely on information functions, such as, for example, the SHE method uses the Shannon entropy, and the PWKL uses the KL information to select item. But these parametric indices are functions of item parameters, so the item calibration is a must if we will implement a parametric CDCAT system. But the problem is that sometimes we don't have a large sample to guarantee the quality of item calibration, and it will cause a problem that the information indices cannot be calculated accurately, so the item calibration wouldn't be optimal. So, and our non-parametric CDCAT procedure can be a good choice because it doesn't require any item calibration. Okay. So let's take a look at the model. This is the data model, and the item response function is here. So if the examinee masters all the required attributes of this item, so this indicator will be 1. And the probability of a correct response will be 1 minus the sleeping parameter, otherwise the guessing parameter. So this indicator is also called the ideal response and can be written as this form. And we will work with this ideal response in our study. The rationale behind is that we made an assumption that this ideal response is the most likely response in the long run. So how do we estimate the attribute profile in a non-parametric manner? So there are 2 to the power k latent classes, and we would like to classify the examinee into one of all the possible classes. For these 2 to the power k possible profiles of alpha, their corresponding ideal response pattern can be constructed in this way. Then the estimator of the proficient class will be will be obtained by minimizing the distance between the observed response and the ideal response. We would like to choose one of the ideal responses to minimize the distance function. And because these two vectors are binary, so the distance function can be chosen as the Hamming distance function. Okay. So there are some remarks. This method doesn't require any model fitting because we use the ideal response. And it can be used even when the sample size is 1. Okay, so it works for not only the DIA model, but also the NIDA and the reduced Raman model. So if we would like to select an item adaptively, can be noted that this non-parametric estimate of the attribute profile obtained by the MBC method is the nearest pattern, or can be seen as the most likely proficient class. So in this sense, we can define the second most likely estimate, the second nearest pattern. So now we have 2 attribute profiles, and the goal is then to choose items that can discriminate these 2 profiles, because these 2 are most likely two profiles. So that is, we would like to choose an item such that these 2 profiles have different ideal responses. So what if there doesn't exist any item satisfying the above restriction? The solution is then to find the third most possible attribute profile, and we can discriminate the most possible attribute, this third most possible profile. Okay, to choose an item to discriminate these 2 profiles. And in addition, we incorporate the optimal item selection method for the initial items. In their article, it has been proven that under the DINA model, the classification will be Q-optimal if and only if the Q matrix for examinees satisfy the following form after count swapping. So in this rule, the first item has to be a single attribute item, and the second item can measure one more attribute. And the attribute measured by the first item can take the value 0, has to take the value 0 if the first item is incorrectly answered, and can be either 0 or 1 if the first item is correctly answered. So this rule is for the initial k item. So this is the k by k matrix, and we can note here there is a subscript I because it's adaptive testing, so there doesn't exist a common Q matrix for every examinee. Different examinee receive different items. Okay, and addition, if this metric is an identity matrix, it's a special case. It's a complete Q matrix. So, in this theorem, this Q optimal means this inequality. The probability of a correct classification is greater than the probability of any misclassification. This means it's Q-optimal. So the algorithm of the NPS method is that we start, and for initial k items we adopt the Q-optimal selection, and from the k plus 1 item, we first estimate the latent class, and we find a candidate profile. So and then we select a discriminative item, and then we go back to the non-parametric classification method to update the proficiency class, and then we go on. So the simulation we conduct is we would like to compare the recovery rates of the NPS method and two parametric algorithms, SHE and PWKL, under the data model. And across all conditions, 3,000 examinees of uniformly distributed skill classes are generated. And the sample size for calibration is 50 or 100. Because in the previous study of CDCAT, item parameters are always seen as norm, but it's not reasonable in small educational programs because we have to do the calibration. So we have set these two levels of sample size for calibration, and the number of attributes is 5 or 7. The test then is 3K, 3 times K, and the size of item pool. The item pool has 300 items, and we construct the item pool by a simple mechanism. Each element of the Q matrix of the item pool follows a Bernoulli distribution with success probability is equal to 0.25 or 0.5. Okay. In the 0.25 case, there will be more single attribute items in the item pool, but in the 0.5 case, there will be less single attribute items in the bank. So and the item parameters are generated uniformly from a less noisy case or a more noisy case. So this is the result. This is a less noisy case, and we have 5 attributes in this condition, and the calibration sample is 100, it's median. And we have a random selection as the baseline, and the above 3 lines are the compared methods. So in this scenario, the SHE performs the best, but it's interesting that the NPS performs better than the SHE method when the item bank has less single attribute items. Okay, and when the calibration sample gets smaller, the discrepancy between the SHE and the NPS gets smaller, and on the right, it's similar. And when we have 7 attributes, okay, the discrepancy between the NPS and the NPS and the SHE becomes smaller, but on the right, the NPS outperforms the SHE method. So if K gets larger, the NPS will perform much better than the NPS, the parametric method. And when we have a much smaller sample for calibration of the NPS method and the SH method performs almost the same, and on the right, the MPS outperforms the parametric method. Okay, it's a more noisy case. The SH method performs the best on both sides. But when the size for calibration, sample size for calibration is small, the MPS performs better than the SH method on the right if the item bank has less singular attribute items. And when we have more attributes, the MPS performs the best on the right, but the discrepancy between these two gets smaller. Okay, is similar. The MPS performs the best on the right. So, we conclude that the number of attributes, when the number of attributes is larger, the MPS performs relatively better than the parametric methods. And when the calibration sample size is smaller, the MPS is a good choice, would be a good choice. And there is an issue, there is an item bank design issue because it's interesting, we found that the right side and the both sides have different impact on the performance of these methods. So it's a question of interest, of our interest. Okay, so and conclusion: when item calibration is not affordable in a small scale setting, the MPS will be a better choice as long as the Q metric is correctly specified. This is the requirement. We have some future research direction. There is a simple possible adjustment for a method. We can define the ideal response in a disjunctive manner, like this. For example, Dino model is a disjunctive model. And then we can develop a disjunctive MPS. That is, for initial K items, there is a disjunctive Q output selection in their article, and we can use this ideal response to select item after the K plus 1th item. So, and we are going to utilize the various distance functions to refine the method. And we would like to investigate the performances of the MPS on the various models. Okay. So here are some select references. Thank you. So, any questions or comments?
Can I say your distance function?
Distance function. It's a very simple distance function. Yes, I mean distance.
I think your non-parametric method depends on how you choose the distance function.
Yes.
And especially the timing distance, like they do consider how each attribute is the frequency of each attribute in the population.
Okay.
So it's like in parametric model, you will consider the probability of this attribute to be really mastered, kind of considering the population distribution. But timing distance kind of considers everything equally. Like your simulation models generate something in favor of the timing distance.
Okay. So yes.
The distribution is far away from each attribute.
Okay. So you mean the distribution of the skill classes, and in our case, it's uniform. So this uniform ham distance,
In your simulation.
yes, in our simulation,
But
we actually
it's
provide
not uniform.
this is uniform. Okay, so it's a question we can deal with in the future.
Yeah, I have a question. I don't quite understand. So it means when we use the Hamming distance, actually it has nothing to do with attribute, right? Because the Hamming distance is used to measure distances between datum profiles, not datum, observed profiles, item profiles, right? Item responses. So it's just the
That will also be affected by the distribution of attribute profile.
right.
I'm not sure. Maybe if you change the simulation.
Yeah, sure. We will do that. We will, here we only do the uniform. But in the future, of course, we will do the,
Actually, you mentioned the weight
Yes.
distances and
and for the weighted distance, we can consider the difficulty of items. So that will be another choice.
So, any further question? Okay, so